Welcome to Spotter Training 2016, produced by the National Weather Service in Des Moines. This video is the second in a two-part series and will include thunderstorm fundamentals, a look at updrafts and downdrafts, tornado formation, and a quiz to test your comprehension at the end. In a separate video, part 1, that will look at an introduction to being a storm spotter, spotter safety, a look back at 2015 Iowa weather in review, and a recap of Iowa severe weather climatology. Thunderstorm fundamentals, we'll look at thunderstorm ingredients and the thunderstorm life cycle. Regarding ingredients, several things are needed to form thunderstorms, and three of those things are moisture, lift, and instability. Moisture is an obvious requirement that's needed to form clouds and precipitation. This moisture source for Iowa often comes from persistent southerly winds and the Gulf of Mexico. Lift is needed that forces the air to rise. That can be in the form of a cold front, warm front, or even a smaller scale feature such as outflow from a nearby thunderstorm. Instability is needed as well and is a necessity for the storm's updrafts to grow. The air needs to be warmer or less dense than its surrounding air to continue to rise. In stage 1 of a thunderstorm formation, the development stage, air rises, cools, and condenses into a cumulus cloud, which often has a cauliflower appearance. The rising air within that cloud or storm is known as the updraft. During the development stage, clouds droplets collide, grow larger, and descend toward the ground. These falling drops form in the storm's downdraft, and the storm then enters stage 2. Stage 2, the mature stage, includes both updrafts and downdrafts at the same time. The updraft part of the storm often has a flat base with rising air into it, while the downdraft often includes rain or hail. This is the most important stage, since this is when the majority of severe weather occurs and the storm is maintaining itself with both rising and sinking motion. In stage 3, the dissipating stage, the downdraft cuts off the storm's updraft and the storm begins to dissipate. You'll notice in these images that the storm no longer has the cumuliform or cauliflower appearance and looks much more fibrous. The severe weather threat during this stage rapidly decreases. Here's a look at the life cycle of updrafts and downdrafts, courtesy of the Iowa Environmental Mesonet at Iowa State University and a webcam from KCCI TV. In this time lapse, over the span of about 40 minutes, you can see updrafts and downdrafts all at the same time. We'll go through this several times here. You can see the flat base in the center of the video with the rising cumuliform appearance above it. Then the downdraft forms in the form of light rain. These updrafts and downdrafts should be readily available for you to view, even during storms that are not severe, and can even be found in lower end showers. So be sure to practice looking for these updrafts and downdrafts, whether you're driving to work, out in the yard, out in the field, or whatever place in Iowa you enjoy looking at the weather. We'll go back through it one more time. You can see the flat updraft base, the rising cumuliform cauliflower appearance, and then the downdraft forms and the storm enters the dissipation stage. Now let's take a look at updrafts and downdrafts in some more detail, including rotating updrafts or supercells, and the location of updrafts and downdrafts, including updrafts in the rear or southern flank of the storm, or in the front, forward, or leading edge. Rotating updrafts or supercells are often a dangerous storm consisting of a single quasi-steady rotating updraft and typically last longer than 10 to 20 minutes. They can be in the front or rear of the storm, and these rotating updrafts or supercells can lead to the production of very large hail and violent tornadoes. Taking a look at this video example, you'll notice the rotation from left to right in the foreground or front of this rotating updraft and right to left in the back. The downdraft is in the front of the storm and in the distance, and you can see that in the gray rainy area. So taking a look at this storm rotate over several minutes, you'll be able to see this rotation quite easily if you watch it for just a little bit of time. The motion is counterclockwise from left to right in the front and right to left in the back. So you can see these cloud features slowly move as they rotate around this rotating updraft or supercell. If you're in doubt whether an updraft is rotating, it probably is not, because it requires you watching it for several minutes, and you'll be able to see this rotation quite easily if you watch it for 5, 10, 15, or even 20 minutes if you have the time to follow the storm as it goes along. We'll take another look at it here. So again, we'll see this rotating updraft underneath the supercell thunderstorm. The downdraft is in the forward part of the storm in the distance. This is the rear or southern flank of the thunderstorm. So you'll be able to see this rising motion and rotation underneath the updraft area. Again, it's moving left to right in the foreground and right to left in the background. As we mentioned earlier, these updrafts can come in a lot of different locations of the storm, but we've grouped them into two basic areas, and spotters need to identify these updrafts and downdrafts, and we can group them into rear flank updrafts and forward flank updrafts. The rear flank updrafts are often more discrete or individual cells, while the forward flank updrafts often occur in multi-cell squall lines or systems such as that, or possibly even a high precipitation supercell. Starting with the rear or southern flank updraft, these cells are typically more discrete or isolated. They can be slow or fast moving, and the downdraft occurs toward the front or forward flank of the storm. So in this case, the storm is moving left to right. You have the updraft denoted by the rising brighter red arrows, with a weaker flanking line updraft on the left. But the main updraft tower is connected from the flat base of the storm through the cumuliform cauliflower appearance, through the anvil, and to the overshooting top. The storm motion is left to right with the steering winds aloft, and the wind shear blowing the downdraft into the forward part of the storm, and this is where the downdraft occurs. There can be rain, hail, or possibly a shelf cloud. Again, in this case, the storm motion is left to right. Now, in the case of a rotating updraft or a supercell, many of the features are the same, but we can see this updraft start to rotate, and you'll see the striations of the storm, and maybe even some rotation in the base of the storm in the form of a wall cloud, or in the worst case scenario, a tornado. Taking another look at these storms, again, these updrafts are in the rear or often southern flank of the storm. The updraft has a large flat base. There's heavy rain in the forward part of the storm, the forward flank, and large hail is possible between the updraft and downdraft interface. The updraft tower is often more readily apparent due to this strong cumuliform or cauliflower appearance. So again, the movement of this storm is from left to right. We have the updraft region, which can be rotating. The winds aloft and the shear blow the downdraft ahead of the storm, and the downdraft occurs in the forward flank. Now, between this updraft and downdraft is where the action area is. That could be where the large hail forms, the rotating wall cloud, or in the worst case event, a tornado. Now, flipping the motion around, this is the exact same type of storm. We have an updraft in the rear flank of the storm and a downdraft in the forward flank, but in this case, the storm motion, as you can see from the arrow, is more from right to left. So this is still the rear flank of the storm, but the steering winds and the shear have blown this downdraft over here, where there's this milky gray appearance. So this is the forward flank of the storm. Instead of moving from left to right in the previous screens, it's now moving right to left. We're looking at the back of the storm as it moves away from us. Spotters shouldn't really get tied down to directions too much. You should be more storm relative, thinking of where the updraft is in relation to where the storm is moving. So the rear flank is often on the south, but the rear portion of the storm is what needs to be emphasized. The storm could be moving toward the southeast, northwest, or anywhere in between. So in this classic diagram here, you'll see the hook echo in the bottom right, which is indicative of a rotating updraft, or at least one of the indications. And you can see in this schematic the rotating supercell, where UD stands for updraft area. So we've got rotating motion here. The storm motion is from left to right, the movement. And you can see the updraft in the rear or southern part of the storm and the downdraft in the forward flank. And this is what you often see with the storm moving from west-southwest to east-northeast. However, the storm could move from the northwest to the southeast, and again these features are the same, with the rotating updraft in the rear part of the storm and the downdraft in the forward flank. So don't get tied down to whether the storm's moving from southwest to northeast or northwest to southeast. It's the rear and the forward flanks that spotters need to identify. Now let's take a look in more detail at the leading downdraft. Even weak storms can produce locally damaging winds in the leading part of a downdraft of a storm, and that's called a microburst. They can be caused by a small-scale downdraft that hits the ground and spreads outward. Winds can be fairly strong, up to 80 miles per hour, even higher at times, and very small scale, only a few square miles in size, and they could last for less than 5 minutes or so. So they're very difficult to detect on radar, and that's why spotters are very important. You can see in the schematic the downdraft and rain falls out of the storm, hits the ground, and spreads out in all directions. Let's take another look at a video from KCCI TV and produced by the Iowa State University Iowa Environmental Mesonet. This is from Lake Panorama. So we can see this downdraft hit the lake. Notice the time as we cycle through this again. It takes a very short time for this downdraft. It's a very small scale and short-lived. So the video starts at 6:19. We'll see this downdraft in the distance, the boat's seeking shelter, and here's this rain foot as the downdraft hits the ground and spreads out. We could see some wind gusts, very strong wind gusts with this passage. It goes through the pier there and across the lake. You can see the sun already, and the storm is all but gone, and that's only by 6:38 p.m. So you can see it lasts a very short time. Now, one of the signs of a microburst is called a rainfoot, and that's when this rain or hail or maybe a combination of both hits the ground and spreads out. It has nowhere to go when it hits the ground, so it makes this foot-like appearance where it hits the ground and curls a little bit at the edge. That's why it kind of looks like a foot and gets that name. But it's a pronounced outward deflection of precipitation near the ground. It could be a rainfoot when there's a lot of rain with it, or something that's called a dust foot when a lot of the precipitation has evaporated before it reaches the ground and there's nothing left but the wind. Now let's turn our attention to forward flank updrafts, which can be found in squall lines and HP or high precipitation supercells. In this case, the updraft is on the leading edge of the storm, and it can take the form of a line of storms where the individual downdrafts merge together and form what's known as a squall line. The leading edge of this continuous downdraft can also be called the gust front, and this gust front produces a signature cloud known as a shelf cloud, and it typically forms along larger scale features such as frontal boundaries. So if we look at this schematic in the bottom left, we can see the rising motion denoted by the red arrows is now in the front of the storm, and the sinking motion or the downdraft is in the back. So spotters need to figure out where the rising and sinking motion is in the storm in relation to its movement. In the top left, we can see our radar depiction of a squall line, and we can see some outflow denoted out ahead of it, but the rising motion in this case is on the leading edge of the system. As mentioned before, these squall lines can often produce shelf clouds, which may extend across the entire horizon. They're often associated with squall lines, but they can occur with smaller individual storms, regardless of where the updraft is located. They are often, however, on the leading edge of the line, or near the gust front, and the updraft occurs right above it. They are long, flat, and often slope downward away from the rain. Remember that for later. Shelf clouds will slope downward away from the rain. And remember, there's no vertical rotation. Spotters often confuse shelf clouds with wall clouds or funnel clouds or other features. They often extend across the entire horizon, and they slope downward away from the rain. They are the interface between the updraft and the downdraft on the leading edge of the storm where the air rises into the storm. Let's take a look at a shelf cloud in motion. Again, we're back at Lake Panorama. The same webcam, and we look across the distance, and we'll see the shelf cloud approach the camera. Notice how the wind rapidly increases as the gust front and downdraft moves through. So initially we have weak winds across the lake from right to left, and then here comes the shelf cloud. This is the interface between rising and sinking air. The updraft goes over us, and we can see in the distance the rain, that's the downdraft. The wind starts to change direction, blows across the pier and the boats, and you can see the trace of that through the water. We'll loop through this again, and we can see this sequence. Here comes the shelf cloud approaching from the distance. This is the leading edge of the storm, and the air is rising into the storm above this feature. The downdraft, however, near that updraft-downdraft interface, produces this elongated shelf cloud, and that's the demarcation between air going into the storm and the downdraft. So the air has rushed up into the storm, the updraft region passes. Now we're in the downdraft region, blowing towards the camera, across the boats, and that's where the heavy rain occurs in the downdraft. Hazards associated with squall lines, there can be several. They can produce widespread damaging winds, as this example was shown from July 2011. They can produce moderate-sized hail, very heavy rain, and occasionally tornadoes that can be weak and fast-moving. But the thing to remember is that widespread damaging winds are often the primary hazard and can produce tornado-like damage. In these images you see here from July 2011, you can see the structure nearly obliterated there with all the damage and the debris blown in the same direction to the top left of the image. And the other image here, you can see the winds were strong enough to take the roof and much of the second level of the structure away. So straight line winds can reach 80 to 100 miles per hour and can produce tornado-like damage. Updrafts can also occur in the forward flank of the storm in a type of storm called an HP supercell, and these, remember, are when updrafts are rotating. The rotating updraft is on the front of the storm. It often includes heavy rain, which can obscure the wall cloud, and tornadoes if they are associated with this storm. They are common in Iowa and difficult for spotters to see all the details of what's going on. You can see in this artist rendition of the front of a HP supercell. The storm is moving towards the person here in view. You can see the cauliflower or cumuliform appearance of the rotating updraft and the striations within the rotating updraft. So those are some clues that the updraft is quite strong and rotating. Taking a look from the top down, we can see the large rotating updraft notated by the hashed area here. That's the large rotating updraft in the front of the storm. It may have a shelf cloud along the gust front. It can produce extremely heavy rain, may cause flash flooding, and tornadoes may be hidden by the rain. These HP supercells can often transition to squall lines too. You can see the heavy rain area with the downdraft in the back is more of a kidney bean shape rather than the hook echo we saw in the previous example, and that's because there's so much rain that the rotation is wrapped around the back, strengthened, and become more prevalent. And the forward flank updraft has transitioned to that part of the storm rather than the southern part or the rear of the storm, and so the updraft and inflow region is now in the front. And if you were a spotter, you would be looking right into the storm to see if you can find a wall cloud or tornado threat. Here's a video example of what an HP supercell would look like with the storm moving toward the videographer here. You can see the striations of this large rotating updraft, the heavy rain in the middle. Unfortunately, it's really difficult to pick out details of what's occurring, say down this road. If a car was driving down this road, you would know you're driving certainly into heavy rain, but you would not know if there's a tornado or if there's hail or how large the hail would be. You can see that gust fronts and shelf clouds can accompany HP supercells in this still image on the right. So remember that all shelf clouds are not necessarily associated with squall lines. So here's a comparison image of the updrafts and downdrafts depending on where the updraft is in relation to the storm movement. In the picture on the left, the updraft is in the rear part of the storm, and the storm motion is from left to right, or generally southwest to northeast. On the right, or a forward flank updraft, the storm motion is left to right, maybe northwest to southeast. As we progress further, we can see this is where the updraft is in the rear part of the storm, with the downdraft in the forward flank as this moves from southwest to northeast. But in the case of the squall line or the multi-cell cluster on the right, the updraft is on the leading edge of the storm, covers a wider area, with the downdraft in the back. Now remember, we noted before that the most probable location of active severe weather, it could be large hail or a wall cloud or even tornado, is near the updraft downdraft interface. So you can see where these updraft and downdraft locations are, and we'll progress forward and highlight in pink. That's the hazard zone where this between the updrafts and the downdrafts, and that's where tornadoes, wind, and large hail can form. Now we'll turn our attention to wall clouds, which kind of look like shelf clouds but are much different in how they relate to the updrafts and downdrafts of the storm. Wall clouds are associated with the updraft portion of the storm. Remember, shelf clouds are with the downdraft, and they're an isolated cloud attached to the bottom of the updraft, and they can be associated with both severe and non-severe storms. Here's a look at a rotating wall cloud, which is very similar to what we saw earlier in the presentation. Signs of a wall cloud include a visible rotation and rising motion into the cloud. And as we mentioned before, these rotating supercells, which can produce a wall cloud, last for 10 minutes or maybe even longer. Strong winds often rush toward the wall cloud, which is inflow into the storm. So again, we can see this rotation moving from left to right in the foreground and from right to left in the background with a big broad rotation like this. Again, this is readily apparent. If you as a spotter are in doubt about whether a storm like this is rotating, it probably isn't. You've got to note the cloud features moving left to right in the foreground and right to left in the background with this broad rotation. As we loop through it again, you'll see this rotating updraft in the foreground, and then the rain and the hail or the downdraft is in the front or the forward flank of the storm behind these signs. This video is courtesy of WITV Local 5. So notice the flag here blowing from left to right. This is the motion in the front part of the video. And in the back it would be moving right to left and then around to the front again in a broad motion. You'll notice eventually, as the video pans to the right, you'll see more features that indicate this motion. Again, look at the flag here on the left, and then another flag pops up here on the right. So this is the left to right motion in the front of the storm and right to left in the back. This cloud is pretty near the ground, had not produced a tornado as of yet, but was definitely a rotating wall cloud. Now we'll turn our attention to funnel clouds, which are sometimes confused with other features, such as shelf clouds or wall clouds. But some things to remember about funnel clouds is that they are narrow tube-like clouds extending down from the base of a storm or wall cloud. They are often vertical. They will be rotating. That's highlighted in red for a reason. If it's not rotating and rotating fairly quickly, then it's probably Scud or some other cloud feature. They're often smooth in appearance. And remember, if the funnel circulation comes in contact with the ground, it becomes a tornado and is no longer a funnel cloud. So to differentiate between the two, you're going to look below the funnel for swirling dust or debris as a tip that has become a tornado rather than a funnel cloud. Now a tornado, we'll look at the life cycle of such, locations in storms, variations, and false nados or lookalikes. But remember, the definition of a tornado is a violently rotating column of air attached to a nearby shower or thunderstorm and in contact with the ground. Remember, a visible cloud or appearance of a funnel is not needed, so you as a spotter just need to look at these two things. It's a violently rotating column of air. It doesn't necessarily have to be a cloud. It often is, but it's a column of air attached to a shower or thunderstorm and in contact with the ground. So spotters need to look for this rotation at the cloud base and on the ground and be able to connect the two. It doesn't necessarily need a cloud between the two. So let's take a look at this example from near Hardy, Iowa in 2014. So as a spotter, you're going to look for the connection of rotation in the cloud and to the ground. So at least we have a funnel cloud here. You can see this rapid rotation. It's rotating quickly, it's vertical, it's fairly smooth, it's not ragged. So this is the funnel cloud we have aloft. So that's item 1 that a good spotter picks out. Now item 2 is going to be whether there is a connection on the ground, and to the untrained eye or someone that has not been through spotter training, you're going to say, no, it's not a tornado, I don't see any cloud connecting the two. But as we loop through this video again, I'll give you another chance to pick out these features, and we'll see that this is indeed a tornado rather than just a funnel cloud. So we'll look through this one more time. As we mentioned before, we certainly have a funnel cloud and rotation in the cloud base. Now let's look on the ground. Right there where the cursor is, we can see the rotation on the ground behind the barn. As it comes out the left side of the barn, we can see this rotation and dust and debris swirl on the ground. So even though there's no connection between the two in the form of a cloud, this does meet the definition of a tornado and is certainly a tornado. So there's this connection of dust to a rotating wall cloud, and this is what meets the definition of a tornado. So again, you don't necessarily have to have this cloud connection between the two. So that's stage 1. We'll go to stage 2, which is more mature, and this is what most people recognize when that cloud or condensation funnel has matured between the rotation in the cloud and on the ground. And this is Belmont, Iowa from 2013. So we can see this widening funnel. Notice it's vertically oriented and it's definitely on the ground. We can see this dust and debris. So this meets the definition of a tornado. If it's completely on the ground and connected to the rotation in the cloud, it is a tornado, and this tornado is likely at its strongest stage when we can see this strong rotation and this dust and debris on the ground. Now in the dissipating stage, it still meets the definition of a tornado, but it's a little bit less pronounced and thinner. It can take on this rope-like appearance before it dissipates, but remember, it's still a tornado. We have the dust and debris on the ground, and you can trace the rotation up into the cloud base. So as we go through time here, we'll notice the storm continue to weaken and the tornado become less prevalent. There is still rotation on the ground, but again, the cloud goes away between the two, and then eventually here in this dissipating stage, there's no longer any evidence of a funnel cloud or any rotation at the cloud base. We still see this dust and debris on the ground. This could meet the definition of a Gustnado as it continues to swirl around the ground. We'll talk about those later in the talk. But remember that what meets the definition is that there's rotation in the cloud and on the ground, and we've lost one of the two in this case. The rotation in the cloud is no longer apparent. So reviewing some tornado locations in storms, we can remember they're in the rear flank. They could be in the forward flank in an HP supercell. They can be in the leading edge, like in a squall line, or sometimes in a very weak storm centered directly underneath the developing storm. These often don't last long, but they can occur. So remember, the bottom line is that tornadoes can form in various locations depending on the storm type. So that's a key for you as a spotter to pick up where the updrafts and downdrafts are. Are they in the front or rear part of the storm? And remember, those are the action areas between the two, the updrafts and downdrafts. Going back to supercell thunderstorms, they can take on a cyclical appearance where they often form in tandem with each other, where one diminishes and another one strengthens. So it's a special form of a supercell that can produce more than one tornado at any time. And you can see here in this image we have the older tornado on the left and a new one forming on the right between the inflow areas and the rear flank downdraft, which is where the air on the backside of the storm kind of cuts off the inflow to the existing tornado. You can see another example here in the bottom right of two tornadoes occurring at the same time. So this occurs when the old tornado weakens and dies and a new tornado forms out ahead of it and gradually transitions from the rear to the more forward flank of the storm. We can have multi-cell lines produce tornadoes. They're often smaller and faster moving. They can form at the leading edge of a squall line along the gust front, often short-lived, but can still be damaging. These tornadoes are often rain-wrapped and very difficult for spotters to see. They can come and go very quickly as well, so they're very difficult to warn for and detect on radar. Even after the fact, spotter information is great if the storm's coming past. Say you're a farmer and you notice this in the field. Remember that a lot of Iowa's road grids are 1 mile by 1 mile, so you can see in this damaged satellite photo, you can see how very small scale the tornado path was. It went between these two properties, maybe grazed the one on the top left, and left the bottom right one untouched. So these tornadic circulations can often be very small scale, difficult to detect on radar. Sometimes we have a single cell tornado, which are often weaker, and these are not associated with supercells or big rotating thunderstorms, and they're called land spouts. They're kind of like a water spout but over land. They form in the very beginning or developmental stages of thunderstorms or even showers. There could be very little in the way of precipitation, often no wall cloud, and usually just a thin funnel. They're very difficult to detect on radar because they are so shallow and transient. You can see two images here where there's barely anything in the cloud in this rake example and the Stewart example. You can see the cloud between the two. But the thing to keep in mind is that both of these images meet the definition of a tornado because they have rotation on the ground, which is connected up into the cloud. Tornadoes can come in a lot of different shapes and sizes. The worst case scenario is often called a wedge tornado, which is shown in this picture from the Parkersburg, New Hartford tornado from 2008. You can see the rotation in the wall cloud is nearly all on the ground, so it's a very wide tornado, which can be called a wedge. Sometimes they're cone-shaped, much like this one from Rhinebeck in 2014. And the wedge tornadoes tend to be very intense. However, remember, the strength of a tornado cannot be determined by observation. We can have broad circulations that appear very large, which are actually somewhat weak, and skinnier ones, which are rotating much faster and can do much more damage than what a broader, weak circulation could do. Tornadoes can be rain-wrapped as well and very difficult to see as a spotter whether there is actually a tornado within the rain. Here are two examples. Where there's a wide area of rain, and there is actually a tornado in there, and they can be often associated with HP supercells and squall lines, but again, it's very difficult for a spotter to see. The best bet may be to drive down the road and see if there's any power line or transformer flashes, and then eventually wait for the storm to pass and see if you notice any damage in the area where you think there may be a tornado. Tornadoes can sometimes be very difficult to see because they're wrapped in rain. They can be nearly invisible. But remember, they don't have to have a visible funnel. We can see the rotation up here in the top of the cloud, so we know we have that. So a good spotter is going to recognize that and say, okay, I see rotation in the cloud. Now I'm going to look down to the ground. So we can see this rotation here and down at the ground, and look at there. There is rotation on the ground. So even though there's some rain here, there's not a classic funnel between the two. This does meet the definition of a tornado. We have rotation in the cloud, rotation on the ground, and they are connected. So we have a tornado in this case. Definite rotation in the form of dust and debris on the ground. So let's look at some false alarms when we don't have those two features, rotation in the cloud and on the ground connected. They could be Gustnados, Scud Clouds, Shelf Clouds, just to name a few, dust devils, rain shafts, smoke plumes, a tower of some sort, and even a grain elevator. So let's take a look at some of these examples. In the top left image, we can see what looks to be a lot of dust and debris on the ground, but we've got to see if there's a connection up into the cloud. Likewise on the right image. So a swirl of dust on the ground along the edge of a gust front doesn't necessarily mean it's a tornado. It means there's a rotation on the ground which is picking up dust. And this is kind of a cousin of a dust devil or a leaf tornado or a little snow tornado you may see in the wintertime. These are all very shallow circulations and not necessarily connected to the cloud base. And they're caused by wind surging out from a storm or some very low-level shallow shear, and they're not, that's bolded and underlined, not connected to the cloud base, unlike a tornado. The winds in a gustnado can still be strong and damaging, however, and if you're uncertain as a spotter, you're not sure what it is, you can report that uncertainty. Say, I'm not sure whether this is a tornado or a gustnado. I see the rotation on the ground. I'm not sure whether it's connected, but I'm definitely seeing rotation and some dust and debris on the ground. So to pick out the difference, it's not always easy. In fact, many times it's quite difficult. So the answer is not always clear-cut. Both tornadoes and gustnados can form at the leading edge of a storm. And to tell the difference, again, you've got to look at the clouds above the dust swirl. Is there a connection? If they are rotating there as well, then you likely have a tornado. So you can see in the image on the left, this is a gustnado. There's no wall cloud. There's no rotation. It's very fragmented looking. The middle one, it's really difficult to tell. It kind of fades, and you really can't tell whether there's rotation at the top. On the bottom one, on the bottom right, there's rotation on the ground connected right up to the cloud base where there's rotation. You can't really see this in still images, but that is definitely a tornado. So as a spotter, you don't need to have a clear-cut answer each time. If there is uncertainty, don't be afraid to report that uncertainty too. Now, scud clouds, these are often reported as tornadoes or funnel clouds by the untrained eye. But remember, as a spotter, we're going to look for things to differentiate between whether these are rotating or not, or whether there's debris in the ground. So they look like ragged clouds on the underside of the storm, but they are not, again, bolded, underlined, not attached to the main storm base or the updraft. They can resemble wall clouds, funnel clouds, or tornadoes, and they're often short-lived, and they do not exhibit vertical rotation. So they can be low near the ground, they can be ragged and fragmented, and look like they're actually on the ground, but they're not rotating, and there's no rotation connection between the cloud and the ground, no dust and debris on the ground, then they're likely a scud cloud. Now, a shelf cloud can also be confused with a funnel cloud or a tornado. Although the long flat cloud along the front of a storm does resemble a shelf cloud. And when viewed from up close or at night, they can be mistaken for a funnel cloud. The shelf clouds often can show some very, very weak rotation, but it's in the horizontal, not the vertical. So there can be fingers coming down that look like a funnel cloud. The shelf cloud may look like a somewhat of a funnel, but if they're not rotating and there's no semblance of dust or debris on the ground or rotation back up into the cloud, then they're not a tornado or a funnel cloud. Another tornado look-alike is a dust devil, and these can be found certainly in Arizona or the desert southwest, but they can be found in Iowa as well. They form on hot, dry days, often with fields either not planted yet or already harvested in the fall, and typically occur on these warm, dry days with light winds. They can extend several hundred feet into the sky. Remember, the winds are usually light and don't cause any damage, but you can really see these compact, tight circulations, but remember, they're not connected to the cloud base of any form, so they're not a tornado. There's plenty of blue sky above this one. They can also be generated by fires. The image on the right is from a prescribed burn in Johnston several years ago, and that's produced what's called a firenado, where the heat from the fire starts to swirl, and it's very unstable in the low levels of the atmosphere. There's a little bit of wind shear, and we get that going even though there isn't a cloud in the sky. So these are kind of cousins of tornadoes, but certainly not a tornado. Now, rain shafts and smoke plumes can also look like tornadoes. Remember, as a spotter, you're going to look for rotation in the cloud and whether there's rotation on the ground and any dust or debris on the ground. So we'll go through some things here. So as a spotter, if you're unsure, the trained eye is going to look for these features for a few minutes, not just a snap. Some of these examples are difficult to see because they're still images, but you're going to watch it for a little bit as a spotter. You're going to see, is there rotation about a vertical axis? Is the feature attached to the cloud base? Is it in the right location of the storm? Is it in the updraft area or near the updraft area? And is it lofting dust or debris from the surface? So if the answer is no to any of these questions, then it is probably not a tornado. We'll go through this example here. This is an example where we could get a lot of reports at the Weather Service of a tornado, but you're going to look for a lot of things here. You're going to say, is it rotating on a vertical axis? It looks vertical, but there's no sign of rotation here. There's cloud elements just drifting along. They're very fragmented, not laminar. There's no rotation in the cloud base or on the ground. We don't see any dust and debris on the ground. So even though it's low-hanging and it looks ominous, it's not clicking these check boxes that we have as a spotter. No rotation on a vertical axis, no rotation on the ground or in the cloud. No evidence of an updraft into this area either as well. It's probably on the leading edge of a downdraft, as a matter of fact. So the answer in this case would be no. We'll look again for some quizzes here and try and test your knowledge of what we've learned while going through this video. So look at the images on the left and right. We'll start with the left. Remember that wall clouds slope downward toward the precipitation. They're associated with the updraft. Shelf clouds slope downward away from the precipitation and are associated with the leading edge of the downdraft. So Try and put in your mind what you think the answer is there on the photo on the right. Your three choices are funnel cloud, tornado, scud cloud rather. And what do we have? Rotation? It looks like yes we do. Is it smooth and laminar? Yes it is. Is it connected to the ground? Well, I don't see any rotation on the ground. There's this rotation up into the clouds, so we do have that connection in the cloud. I don't see anything on the ground, however, so that will rule some things out. We'll go through here. So remember, on the image on the left, that is a wall cloud. So this is the rotating updraft. This is from Johnston, Iowa several years ago. That's a rotating updraft. And we have this wall cloud or lowering in the updraft region, and it slopes downward towards the precipitation. So this, if you go back earlier in the talk, this is a rear or southern flank updraft, and the forward flank downdraft is here on the right. So the storm's moving from some form from left to right. So we have the updraft region, the shear and the steering currents are blowing it downwind here. So this is the cycle of air through the storm, downdraft, and then back up into the storm. That's why this wall cloud, or it could be a tail cloud, is sloping into this rain here. Clouds like cool and moist areas to form, so they probably have a little bit of both going on here because of the rain-cooled air and the downdraft. So we have this cycle, rotating updraft, up into the storm, blown downwind into the downdraft. So this is a wall cloud rather than a shelf cloud because the cloud is pointing downward toward the precipitation. Now on the right, your choices were funnel cloud, tornado, or scud cloud. And the answer here is funnel cloud. We do have this laminar vertical rotation connected to the cloud base, but there's no evidence that it is reaching the ground. The next quiz here, you make the call. This is kind of difficult to pick out, but right off the bat we can see there's dust and debris on the ground. So at a minimum we have rotation there on the ground. Now whether it's connected to the cloud base, that's the big question. Remember, the definition of a tornado is a violently rotating column of air from the cloud base to the ground. We don't really see much of a connection between the two, so we're going to look up here and cycle through this again. We can see right here is where it's rotating. It's difficult to pick it out, but if I tell you it's rotating in the cloud and there's dust and debris on the ground, that's going to mean your answer is what between these four things? I don't see any rain. It could be a Gustnado, but if I tell you there's a connection to the cloud, then it's going to be a tornado. Again, tough to determine in real time, but there is weak rotation in the clouds above the dust swirl. Here's another example. Difficult to tell. This is a storm chaser from the Into the Mezzo team here in central Iowa, courtesy of Willard Sharp. And we can see some things in this video. We can see rain. We can see some low-hanging clouds. So right away, nothing of significance to start, but we'll watch it a little bit more. And the storm gets a little closer to the car where the video is being shot. And if we look off to the left, we might be able to see some low cloud fragments that would get our attention. So we're going to look and see, okay, are these low cloud fragments rotating, and are they rotating fairly rapidly? Looks like an updraft region. I can kind of see the clouds forming going up into the storm. And suddenly here they notice over to the left, there's the tornado, and this is rotating, moving along the ground. You can see the rotation kind of here on the leading edge of it better. But this is rotating and it's on the ground as it moves. We can see a little bit of dust and debris. It's obscured by rain, so if we tell you all these things, what does that mean? We've got rotation in the cloud and on the ground as it moves along, so that makes it a tornado, and a rain-wrapped tornado at that. Very difficult to see even at that close range. This was from Veterans Day 2015, not that long ago, in Madison County, south of Winterset. Here's another quiz, shelf cloud or tornado. This looks very ominous and mean looking, but we're going to see, is there any dust or debris on the ground? If there was a tornado of this size behind the trees, you'd see a lot of dust and debris. It's very fragmented. It's not smooth and laminar. The image on the right, the same thing. It might look like a wedge tornado at first glance, but there's no dust or debris behind the back. So on the left we have a fragmented scud cloud, and on the right that's a shelf cloud on the leading edge of the downdraft, which you can see from the rain in the left of the image, just to the left of the garage. Here is another example. We'll go through this. Remember, look at those things we're looking for. We're looking for a connection from the cloud to the ground. So we look down the road here, and there may be a little bit of dust or debris in the ground. We have what looks like a funnel rotation aloft. We'll go through again. Zooms in a little bit closer. So remember the definition again of a tornado: a violently rotating column of air in contact with the cloud to the ground. Let's zoom in a little closer. More video. And we certainly have what looks like a funnel aloft. As we take a closer look on the ground, there the person sees this rotation in the cloud, looking to the ground. There's the connection starting to be made further, and we'll look beyond these trees. You don't see it as readily as you did in the first video, but it's becoming ever so close to the ground, and then wham, there's your connection. You've got some dust or debris on the ground. Very weak, but there's dust or debris there. So that makes this a tornado, even though this condensation funnel is not prevalent at all times. Some more quizzes. You look here. So we're going to, also as a spotter, you're going to look for this rotation. You're also going to look where the updrafts and downdrafts are, which we learned earlier in the video. So we can see here in the left image, the downdraft is in the back. So the updraft is in the front. This is a forward updraft. And on the right, we're going to ask you how many tornadoes there are. And remember the definition, there's got to be in contact with the ground. So in this one, we can see certainly it's vertically oriented, it's laminar, it's rotating. At a minimum, this is a funnel cloud. We're going to look on the ground here in this field. Do we see any dust or debris in the foreground circulation? The answer there is not really. So in the background, we're going to ask ourselves those same questions. Do we have this dust or debris on the ground? It looks like we have a little bit of it there, and we have a rotating wall cloud. We have rotation evident up in the cloud. So the answer to the left one is that's a shelf cloud. It's sloping downward away from the precipitation. On the image on the right, we have one tornado. This one is in the foreground. It looks like a funnel cloud, but there's no connection on the ground, whereas we can see the connection from the cloud to the ground in the background one. So what has this training provided during this video? It's knowledge about how to spot severe weather and communicate what's seen to the National Weather Service. More of that can be found in video part 1. Awareness about the inherent dangers associated with severe weather spotting, again in part 1 if you want to review that. Remember and understanding that the National Weather Service does not officially deploy spotters, and that spotters do any chasing or deployment at their own risk, strictly at their own risk. What this training did not provide, there's no certification. We have thousands of spotters in our registered database, and we can't certify whether you learn the material, watched this video through the whole thing and digested it or anything of that nature. So we do not distribute certificates. There's no license to break the law, including traffic laws. You can't be pulled over speeding into a storm and say you're a storm spotter and get away with it. The officer of the law is not going to give you any break in that regard. And there's no official affiliation as a National Weather Service agent or employee. You are doing this strictly on your own and submitting this information into the Weather Service to help your neighbors in the common good, much like it'd be if you saw a fire at a neighbor's house. Doesn't make you a fireman, but it sure helps the cause, and it makes you help protect your neighbors and your fellow citizens. So again, thank you for reviewing this. I encourage you to look through part 1 if you have not already. And if you do spot this season, have a safe year.